Hey everyone, welcome back for the second system design problem breakdown. The first one was Ticketmaster. The reception to that was really positive. That was encouraging. To be honest, I didn't know if I wanted to make these YouTube videos. You all really enjoyed that first one. There were some great comments, so going to try to keep these rolling. I can't make any commitments, but maybe once every 2 weeks or so, at least in the near term, you should see a new one. So the one that we're going to do today is we're going to design Uber. So this is the hardest or the most interesting, in my opinion, of the proximity search problems. If you can do this one, then you can probably do Find My Friends, Yelp, etc. It has a lot of the same common pieces. And this is asked a ton at most of the top companies, frankly. Notably, it's asked a lot at Google and Meta. So I think it's a great one for us to practice. Now, a bit about me as a refresher. I spent 5 years at Meta. I was an interviewer and a staff engineer there. And I'm now the co-founder of Hello Interview. And so Hello Interview is a site that helps candidates prepare for upcoming interviews, largely via mocks with senior FANG engineers and managers like myself. And so I've asked this question well over 50 times, and I know exactly where candidates of all level, from mid-level up to senior director or staff and principal, do well, and where they tend to get tripped up. So we're going to walk through this as if it's a real interview, but I may periodically interject, or I will periodically interject with some tips or frameworks, and really sharing that perspective from a senior interviewer. Lastly, if videos aren't your thing, I've written this detailed breakdown to this problem here on hellointerview.com. So you can come over, I'll link it in the comments, and read this if you prefer. We also have a handful of other breakdowns to common problems, and this list is continuing to grow. So come over here and check it out. All right, without further ado, let's get into it. Okay, first things first, let's touch on the roadmap that we're going to follow throughout this video, as well as the roadmap that I recommend that you follow for any of your system design interviews, particularly those for which you're designing a user-facing product, like Design Uber. So the first thing that we're going to do is we're going to go over the requirements of the system. This is both the functional requirements, the features of the system, as well as the non-functional requirements, so the qualities of the system. We're then going to touch on the core entities in the API. Core entities is similar to what you may be thinking in terms of data model, but it's really what are the objects that are exchanged and persisted in my system. And then the API will use those objects in order to expose the user-facing APIs that allow you to satisfy your functional requirements or the features of the system. Next, we'll sketch out a high-level design. The goal of this high-level design is simply to satisfy the core functional requirements of the system. It should be simple, just to satisfy those core features. And then lastly, we'll go into detail in some deep dives. And the goal of the deep dives is to make sure that our system satisfies all of our non-functional requirements. So this is the roadmap that we're going to follow. All right, so the very first thing that you're going to do is you're going to write down the functional requirements of the system. The functional requirements, as I mentioned a moment ago, are the core features of the system. So these are often like users should be able to statements. Now, ideally, the interviewer has chosen a system that you've used before and you know pretty well. That would be amazing. That would make this a lot easier. In the case that they didn't, you'll need to ask a handful of questions to try to understand that system. Now, I'm going to assume that most of us know Uber pretty well, and it's certainly the case that I do. So the core requirements of the system are that users should be able to input a start location and a destination, and get an estimated fare. So this is what happens at the very beginning when you open up your Uber app. You end up saying where you want to go, it knows where you are, and it gives you a bunch of price estimates, right? It says that for Uber X, this will cost you $32. For Uber XL, this will cost you XYZ. Now, I'm actually going to mark out of scope multiple car types. Oof, bad typing. Multiple car types, and we're just going to do Uber X, for example. So just one estimate. And then the next thing, once you get that estimate, is that users should be able to request a ride to be matched with a nearby available driver in real time. So users should be able to request a ride based on an estimate. Cool? And then the last thing is that drivers need to be able to accept that ride request and then ultimately navigate to the user's location and finally to the user's destination. So drivers should be able to accept, deny a request, and navigate to pick up / drop off. Now, there's different versions of an Uber system design question. In some versions, maybe you don't have the estimated fare part. Maybe you focus more on the actual navigation. This is typically where I lead candidates. It's what I think is the most interesting, but know that it's not all inclusive. So maybe you want to take some moments to yourself to think about what some additional functional requirements maybe, and how you'd additionally include those in the high-level design that we'll get to later. So you saw that I added one thing out of scope here. It's good to clarify some additional features that you might think of, but you're clearly not going to do. It's really important that you stay focused in a system design interview. They move really quickly. So I recommend that you focus in on, at most, those 3 core features of a system, and everything else you put out of scope. So for example, some other things that I could think of is ratings for drivers and riders. I'm not going to handle that. That's going to be out of scope. Some other things is like schedule a ride in advance, right? This is showing my product thinking as an interviewer or as a candidate, but showing clearly that I can prioritize and focus on what matters. So we'll keep it there. The next thing that we do is our non-functional requirements. So the non-functional requirements are the qualities of the system. These are typically like the ilities. So it's scalability, availability, integrity, these sorts of things. Now, most candidates make the mistake of A, rushing through their non-functional requirements, and B, just writing down some of those buzzwords. And I can tell you right now that's both not useful and it doesn't help you with the design later on. So for all candidates, but particularly senior and staff candidates, the non-functional requirements are incredibly important. This is what's going to dictate your deep dives later on. So you want to make sure that you, A, identify the qualities that are unique and relevant to this system. What makes this system challenging? What makes it difficult? And then B, that you're able to put them in the context of this system, and C, ideally quantify them if possible. So for example, what do we care about in this system? Well, we care about low latency as we do in most systems, but in the context of Uber, it's low latency matching, and we can quantify that. So we can say maybe less than 1 minute to match or failure. And so that failure would just be, we give the user a message saying that there's no available drivers in the area. Now, what else is important? We can consider CAP theorem here. So do we prefer consistency or availability, given that partition tolerance is a must? Now, in this case, we actually really care about consistency, but specifically consistency of matching. So we want to make sure that any given ride is only ever matched to one driver. So ride to driver is 1-to-1, right? We want to make sure that there aren't multiple drivers who get the same ride. And for that reason, consistency is going to be incredibly important. Now, on the other hand, we do still care about availability. We care about availability, basically everything outside of matching. So highly available outside the matching. And this means that we're going to minimize downtime. The system is going to be consistently available, reliable. We can process requests 24/7. This is going to be an important component of our system. And then lastly, we should be able to handle high throughput. But again, putting that in the context of our system, this is in surges for peak hours or special events. Like if, a football game or the Taylor Swift concert just got out, you're going to have massive surges there. And so we can try to quantify what our surges might be. And given that we're talking about stadiums or New Year's Eve, surges are probably on the order of hundreds of thousands of requests within a given region. All right. Perfect. And then additionally, we can consider some out of scope here as well. Some additional things that are always worth considering are GDPR and user privacy, but we're not going to go into it in this design, certainly not. Resilience and handling system failures. Frankly, we may touch on that a bit, but it's not going to be the primary importance of the design. Monitoring, always a good thing to have in any design, but we're not going to have it in ours. No monitoring, logging, alerting, etc. And then deployment, CI/CD pipelines. Those are other things that would be great in any design, but aren't going to be the focus of our system. So now we have a really clear understanding of the system that we're going to build. both the core features, being able to get fare estimates, request a ride, match them, and allow drivers to accept or deny those requests, as well as the non-functional requirements, the importance of low latency matching, consistency of matching, high availability outside of the matching context, and the ability to handle high throughput. So from here, we can move on to our core entities in our API. All right, before we move on to the core entities, there's one thing I want to call out, and that's that some viewers might have realized that we didn't do back of the envelope estimations. And you're right. So my opinion here is that in conducting so many of these, the back of the envelope estimations, particularly early on in the design, like right now, are almost always a waste of time. So candidates estimate daily active users, bandwidth, storage, and at the end of those estimations, they look at their numbers and they go, okay, so it's a lot. And then they move on. And at most, they came to the conclusion that it's a scaled system that's going to need to be horizontally scaled, going to need to use things like maybe S3, whatever it may be. But they knew that. They knew that before they started the calculations. So I learned nothing about the candidate during that. They burned valuable time in what's usually just a 35-minute interview when you exclude pleasantries and time for questions at the end. So my opinion here is that candidates should forego the back of the envelope estimations immediately after the non-functional requirements and only do them if the result of the calculations is going to directly influence the design. So here's how I suggest you approach that. When you finish your non-functional requirements, say this to the interviewer. Say, I know a lot of candidates do back of the envelope estimations at this point. It's my preference that I forego them for now, and that instead I do estimations during my high-level design if there are some calculations that I need to do for which the result will have a direct influence on my design. Is it okay with you? And 99.9% of interviewers will say, yes, that's great. You might have 1% of weirdos who say no, in which case, no worries. You'll do your estimations then to satisfy them. But that's my strong recommendation when it comes to back of the envelope estimations. Now, monologue aside, the next thing that we do here is we jump into the core entities. And so you may be wondering to yourself, why does he keep saying core entities as opposed to data schema or data model as you're probably more accustomed to? And the reason is I found that most candidates and myself, when I'm an interviewer, I don't know the full data schema at this point. I don't know all the fields and all of the columns. It's far too early in the design. But I can sketch out what my core entities are. What are the entities that are being persisted? This usually maps one-to-one with the tables or the collections that you're going to have. So oftentimes I'll document the entire schema and the full columns as I'm going in my high-level design, as you'll see me do here today. And I'll start here instead by just bulleting those core entities. And these core entities are going to be useful to inform my API. We'll see that here in a sec. So what are the core entities for something like Uber? Well, I'm going to have a ride object, of course. I'm going to have a driver. I'm going to have a rider. And then this one's maybe less obvious. I'm going to have a location entity. And this location entity is going to be responsible for having the most up-to-date location of all of my drivers so that I can quickly match them based on proximity. And we'll see, of course, how that works in the high-level design. And so now we move on next to the API. And the API's goal is really simple. People kind of overthink this or make this more complicated than it needs to be. We're going to use our core entities in order to go one by one satisfying our functional requirements. So we might have one, we might have many APIs per requirement, but we're going to look at those one by one and make sure that we have a full set of APIs in order to meet them. So for example, the very first one that we have here is to get a fare estimate. And so what this is going to do is it's going to request the ETA and the price of a ride, and it's going to persist those in our database. And I'm going to choose to, instead of use a separate entity, just create a ride entity with an ETA and a price. And that ride entity is something that we can then continue to update if ultimately they decide to request the ride and match, etc. If they don't, we have some excess data laying around, but it'll be great for analytics to know what people are requesting and ultimately not choosing. So this API is going to be a post because we're going to be creating new data. I'm going to have the ride fare estimate, and it's going to return a partial ride. And I use partial here. This is just TypeScript notation. You can use whatever you want. This is not a requirement for the interview. It basically just says we're going to return part of the ride entity. Specifically, the parts that I'm interested in are the ID, the ride ID, the ETA, and the price. And I might mention that verbally in the interview. You might even write it down. And the things that's going to be passed into the body here are just going to be the source and the destination. Basically, where am I coming from and where do I want to go? So we're exchanging our core entities. in order to satisfy our first functional requirement. Easy. Now let's move on to the next functional requirement, which was users should be able to request a ride based on an estimate. So now given that estimate that was just returned to us, we should be able to request a ride. I'm going to use patch since we're going to be updating that same row. This could also be put. It doesn't matter too much. I wouldn't get caught up here. But I'm going to request a ride, and that's going to take in the ride ID that was returned here, right? So that ride that we persisted, that we made an estimate for, that has a source and a destination already, I'm now going to request that I get matched with a driver, and I actually want to go on that ride, and it's going to take in a ride ID. And since this operation is going to be asynchronous, we talked about it taking up to a minute to match with a driver. This is just going to return a 200 or a status code maybe a 400 in case of failure, and it's going to happen asynchronously. Great. Now the other thing to consider is that the actual matching process is going to require us knowing the location of drivers. We mentioned that. So how do we know the location of drivers? Well, we're going to have some additional endpoint here. Maybe it's a location endpoint update that drivers call every n seconds with their lat long to let us know where they are. So that's going to be important. And note, a lot of candidates miss this up front in the API section. That's totally fine. There's no expectation that you get every single API right out of the gate. As you're designing, you might find more, and you'll come back and you'll add to this list. That's totally great. Of course, I've done this so many times. I have the foresight that you might not have in an interview. So I'm going to add it here immediately. But just know, this is kind of a moving model that can be updated as you go. And so now we've satisfied the second functional requirement. The third one is the driver should be able to accept or deny a request, and then also navigate to pick up and drop off. So to be able to accept or deny a request, we're going to go back to our ride API. This is going to be driver accepts, and they'll pass in that ride ID as well as maybe true false or true false if they accept or deny it respectively. So given this ride ID, do I accept or deny matching? And again, I chose patch here because we're going to be updating that same row. Realistically, this could also be a post because it probably will need to create a new row in the status or maybe update a different status. We could come back and change that, but I think patch is going to be fine for now. And then the last thing is that drivers are going to be navigating first to the pickup location and then next to the destination. They need to be able to update us, tell us that I've gotten to the initial pickup location. It's time for me to go to the destination. So I'm going to create an endpoint for that. It's going to be called ride driver. It's going to be update. And what it's going to take is, of course, that ride ID again, and then, some status. And maybe this status is going to be picked up or, dropped off. Doesn't matter, something like that. And what it's going to maybe return is the lat long of the next place that they need to go, or null if not relevant. So in the case that they picked them up from a destination, then we'll update that in the database and we'll send them, cool, or from a pickup location, here's the lat long of the destination you need to navigate to. On the other hand, if they tell us that they dropped off a candidate, then we'll just give them a 200, return null here. There's nowhere further for them to go. Great, so this is a complete set of our APIs. They use our core entities in order to satisfy our functional requirements. A couple things that I'll note quickly, beyond the fact that you can come back and amend these, as I already mentioned, people may be noticing that I don't put any data types here. Why is that? Now, if you're a mid-level candidate or a junior candidate, go ahead, you can put data types, that's fine. Senior staff candidates, please don't. I find that this is a massive waste of time. I see candidates sitting here doing things like this, typing out number, and it's borderline insulting to the interviewer. Maybe I'm being too flippant in saying that, but it's inferred. You're a senior candidate. You're a senior plus candidate. We know that you know that a latitude is a number. We know that you know that a ride ID is either a string or a number respectively. We know that accepting is a Boolean. We know these basic types. So unless you're going to introduce something unique, like I did here in the case of an enum, then maybe it's worth spelling it out. But otherwise, your interviewer is smart. They're following. They've done this plenty of times. Save yourself the time. Again, 35 minutes. It's going to go quick. The other thing to mention is that you'll notice maybe that I don't put user ID in any of these requests. So for example, driver accept, well, how do we know which driver sent this? And so we're going to get this off of the session or the JWT that's in the request header. And this is important for security reasons. I suggest you don't put something like user ID here unless you're explicit with your interviewer that you don't actually mean that you're putting this in the body, but it's in the header instead. Because if we did put it in the body, then any user could say request a ride on another user's behalf by just making this request with the other user ID's with the other user's user ID in the request body. So good API security. We're going to use either JWT tokens or session tokens, and they're going to be in the request header. This is something that I would speak to during the interview. Maybe I would write it as a bullet, but not necessary. Awesome. All right, so we got our core entities and our API down. Let's keep moving. Now for the fun stuff. All right, we've laid a really strong foundation. We've gone over our requirements, the core entities, and the API. At this point, ideally, you're about 15 minutes into the interview. If you're a mid-level candidate, maybe it's taking you a little longer than that, 15 to 20. If you're a senior staff candidate, ideally 15, maybe even a little bit less. And this gives you plenty of time now to go into the high-level design, which we'll do now, while leaving room at the end for deep dives. So we're going to continue on this theme of each section relying on the one before it. So for the high-level design, the goal, as we mentioned, is to be able to satisfy our core functional requirements of the features of the system. And the way that we're going to do that is we're just going to go one by one through our APIs and use them as the input flow of data in order to design a system that satisfies each of them. And if we satisfy our APIs, then we've satisfied our functional requirements because, of course, we built our APIs based on our functional requirements. So hopefully that makes sense. Let's start then, right away, with our first API endpoint. The first API endpoint, again, is post ride fare estimate, which takes in a source and a destination and returns to the user an estimate as well as an ETA for a particular ride request. So what do we need in order to make that a reality? Well, the first thing that we're going to need is a client, and we're going to have a client for a driver. And so this can be an iOS app, this could be an Android app. We won't support web. And so this driver, I've said driver here, I mean writer. So this writer is going to make a request, and that request is first going to hit our AWS managed API gateway. And so this guy is going to be responsible for a couple of things. It's going to be responsible for load balancing. It's going to be responsible for routing. This is the thing that it's kind of most important. It's going to take each incoming API request and it's going to route it to the correct microservice. And then it can also do some additional auxiliary things like authentication, SSL termination, what else can it do? Rate limiting, etc. So it's nice to jot some of these things down. Don't get distracted by them. You know, this shows well for the technical excellence axes that Meta evaluates under, and most of the major companies have something to that effect. But don't let it distract you. It's not the most important thing. So important, I got an AWS API managed gateway here, and it's going to simply be responsible for routing to each of my respective microservices. Now in the case of this request, this is going to be our get fare estimate request. We're going to hit this ride service that we'll create here. And the ride service is going to handle fare estimates. And so the real Uber is going to have some complex ML model that's going to be responsible for getting these estimations. And in the interview, you have a couple options. You could just black box it and say there's going to be some complex model here. This is what we're going to use. Or you can just overly simplify. I'm going to take the route of just overly simplifying, and I'm going to overly communicate that to my interviewer. And I'm going to use a third-party mapping. So this could be like Google Maps. And so this is just going to be an API call that we're going to make here in order to find out, given current traffic, what is the current ETA to get from our source to our destination. And then we're just going to use that ETA in order to estimate a price, maybe a simple multiplication from there. So our writer is going to make a request to get a fare estimate, which is going to hit our ride service, which is going to use a third-party mapping service in order to actually get that estimate. And then we need to persist that estimate in our primary database here. And so I'm just going to label this primary database for now, for primary DB. And this is where I had mentioned earlier that we're going to forego on the actual data schema and the data models until we know more during the high-level design. And this is the appropriate time to do that. So now we're persisting one of those ride objects. And given that I'm so deep into the flow of data, I know exactly what needs to be persisted and what should exist on this ride object. So for example, I know that it's going to have an ID. That's pretty basic. I know that it's also going to have a rider ID. It's going to have a fare that we just estimated. It's going to have an ETA. It's going to have a source. It's going to have a destination. And then it's going to have a status. And that status is going to start right now as fare estimated, right? And we'll have some more things that we add in a moment. And so this isn't complete. There's more things here. And we're going to come back and we're going to add to it each time one of our arrows lands on our database. We're going to see, is there another field that should be written here? And so then the other thing that we'll add, since we added this rider ID, we know that we have a foreign key to some rider object. This is less interesting. A rider is going to have an ID and they're going to have some metadata, probably where their location is, some of their payment information, etc. It's not the most interesting thing for this design, so I'm just going to ... it, which is kind of a great tactic to use to ensure that you don't get distracted. So we've satisfied our first API endpoint. Just to be super explicit about the flow of data, the writer makes a request to get that fare estimate. We calculate the estimate. We persist it in our DB with these fields. Super easy. And then we return back to the user the ID, the fare, and the ETA. Fantastic. Now, the next API endpoint that we need to satisfy is when the user got that fare estimate and on their client, they clicked on it to say, I like the estimate, I want to request a ride. And this is what starts the actual matching process. And this is what ultimately matches them to a nearby driver based on proximity. So to handle that, I'm going to introduce an additional microservice. And this is going to be the ride matching service. And the reason I'm using a separate service here, ride matching service. The reason that I'm using a separate service here is for a handful of reasons. One, the things that these two do are incredibly different. This one's going to be more computationally expensive, and it's also going to be an asynchronous process. And so by separating them, I allow them to scale independently. I allow them also to be maintained by separate teams, and that's going to be kind of effective for this current design. So now the writer is going to make a request. So request ride. It's going to hit our matching service, which is going to be responsible, of course, for matching drivers and riders. And so the first thing that this thing needs to do is it needs to know the location of the drivers. So we're going to have some location DB. Remember, we had a location entity. So we're going to have some location DB. And this is going to store the location of drivers. It's going to be just the current location of the drivers. And so we can make a request here to get driver locations. And this is probably going to be within some radius. So maybe we say, get all of the drivers within 1 mile, 2 miles, 3 miles of the riders, get all drivers within n number of miles of the current rider's location. The rider-driver thing really trips me up. But anyway, hopefully you guys are still following. And so then this begs the question naturally of, well, what about how do we get locations into that database in the first place? And that's where this endpoint came in, right? Location update. This is the API endpoint that drivers are going to call in order to make sure that this location DB is up to date. So we'll introduce now a driver client. That driver client is going to make periodic calls. Let's say every 5 seconds now, just to be easy. Every 5 seconds to a location service that is responsible for simply updating the location of drivers. So this is going to be update location. So it's going to take a driver location, store it in the location DB so that the ride matching service can query it. So the ride matching service then has the eligible drivers. It's going to need to make sure that none of those drivers are currently in a ride or maybe offline. So we can say get status based on driver ID here. So this guy can make a call to this service in order to query our database here for a driver. And a driver is going to have an ID. It's also going to have some metadata like its car, its license plate, their image, all that sort of stuff. But importantly, it's going to have status. And that status might be in ride, offline, or available. Maybe there's some additional ones too, but we'll stick with those for now. So ride matching service got all of the drivers within close proximity and then filtered out those that are in a status other than available. And then it starts sending out requests to them saying, do you want to accept this ride? And the way that it's going to do that is going to be a bit abstracted in our design, but I'm going to introduce this notification service. A notification service itself is an interview question. So I'm going to black box it for now. And this is going to use like Apple push notifications, or I believe Google Android uses Firebase. Am I making that up? Don't quote me on that. But regardless, we're going to use the native push notifications for each of them respectively. Our arrow now is going to be like this. And we're going to send a push notification to the driver's device saying, do you want to accept this ride? And if they choose to accept, they're going to make an API endpoint when they, or an API call when they click on it. They're going to be calling that driver accept endpoint. So that's going to be this accept, and it's going to take in a Boolean. It's going to hit our riding service, and then we're going to update the status of the ride accordingly. And so one additional thing that could be here is, of course, the driver ID. We'll call it optional because it doesn't exist from the start. It only exists once there's a match. And then we would update our status to maybe matched or in ride or whatever it may be, but something along those lines. So that's what happens when the driver then accepts the ride. Yes, and then the very last thing that happens is that the rider needs to know where to go, or excuse me, the driver needs to know where to go. And so we created an endpoint called update for them, where they tell us that the status has changed, and we give them the next place to be. So the driver calls update, it updates their status to maybe they got to the source, they got to the destination, any of those additional statuses, and then we optionally return the lat long of where they need to go next. So if they just got to the source, then maybe their status updates to picked up driver, and we send back the destination. Okay, so at this point, we have a fairly simple design. It should satisfy all of our functional requirements, and we should be able to go back, look at it, and confirm that. Yes, we can request fare estimates. Yes, we can request a ride based on an estimate. And yes, drivers can accept or deny a request and then navigate to the drop-off and pickup location. Now, this design is simple, and it doesn't go into detail in a lot of places where we will need to go into detail, such as how does this location DB work? How does the ride matching service ensure consistency such that there's no double matching of drivers to rides? These are all things that we're going to go into in our deep dive. But for now, we should be able to communicate with our interviewer. I have a high-level design that satisfies my functional requirements. Next up, I'm going to go deep in a couple places to satisfy my non-functional requirements. All right, so our high-level design is in place, and we're going to jump into those deep dives now. Now, if you're a senior or a staff candidate in particular, these deep dives are really where you're going to earn your keep. This is where you're going to show off that you have level-appropriate knowledge. So if you're a mid-level candidate, then what we have on the board right now is pretty damn close to what would be a passing interview. That's probably not quite enough. Your interviewer is going to probe you in some places, maybe as it pertains to the matching algorithm and consistency, or this location DB being sped up, maybe sharding in your primary DB, scaling, etc. You should be able to answer some of these questions to the best of your ability fairly competently. And that's probably around good enough for a mid-level hire. Now for senior, that's certainly not the case. You would now need to go deep to satisfy your non-functional requirements, and you should be able to go deep in a couple of places. Aim for 2 places or so. And then for staff, the expectation is that you can go even deeper. So maybe in more places, say 3 places, but the degree to which you go deep, the depth, is increased. And it's often even the case with staff candidates that you teach your interviewer something. And so this isn't strictly a requirement, but it's usually a really good sign. If your interviewer walks away and it turns out that this staff candidate had a lot more knowledge about, say, DynamoDB, and they were able to go deep in some properties of DynamoDB and how it pertains to this particular system, leveraging their own personal experiences, then that's a really fantastic sign. So we're going to show a couple places where you could go deep and where you could show off that depth. We'll do more than is needed in, frankly, even a staff interview probably. But I kind of want to show the range of places where candidates could go deep here. So as I mentioned, in order to inform where we go deep, we come back to our non-functional requirements, and we can really just go one by one through these. So the first thing is we need to make sure that our system has low latency matching. That's great. So that's going to matter in a couple places, but the place that I want to focus in on first is our location service, because this is kind of a really pivotal and interesting part of our system. So as it pertains to efficiency and cost, for what it's worth, we need this query on the locations DB to get near proximate drivers to be really quick. So note that. And then the additional thing along this path is that this is going to be a lot of updates. So we need this path to be able to handle the number of transactions per second that we're getting from driver updates. And so that's actually where I'm going to start, is I'm going to estimate that. And we talked about in the beginning how don't do math just for the sake of doing math, and you can do it later on in your design when it makes sense, and that's exactly what I'm going to do here. So I know that Uber has 6 million drivers. I'm going to estimate that maybe 3 million of those are active at any given time. For what it's worth, that's probably an overestimate, but we'll go with it anyway. And then we had mentioned earlier that we were going to send updates every 5 seconds. So a driver will send their location update every 5 seconds. So that means that we're going to have 600,000 updates coming into the system every second. Great. So whatever database we have here, as well as this service, is going to need to be able to handle 600,000 transactions per second. Now we'll talk about later in the interview. Realistically, there's other ways to trim down on this, but let's keep that higher estimate for now. Awesome. So let's talk about this location DB. How can we store the location of all of our drivers and make it incredibly quick and efficient in order to look up drivers that are within some radius of them? Well, the most kind of obvious thing that we could do is use some SQL database, say Postgres. We could have a column for lat and long respectively. And then we would just query, range query, in order to determine any drivers that are within a lat and long upper and lower bound. And I guess we would have an upper bound, a lower bound, a left and a right bound, respectively. So 4 total bounds. Now, this sucks for a handful of reasons. The first is that the indexes that we would build here on lat and long respectively are B trees. And B trees are optimized for one-dimensional data. So lat long is inherently two-dimensional, as we just mentioned. And so that's not going to be well optimized. These are going to be slow queries, non-performant queries. And also it's going to require us scanning a large number of rows for wider queries. If we have a region of say 20 miles or something, then now we're going to have to scan a ton of rows in order to get this data. And so that's also bad. Lastly, and why Postgres is just a terrible answer here, is that Postgres can handle maybe 2 to 4K transactions per second. That certainly can change depending on right replicas, optimized hardware, but let's just estimate it's around there. And so if we do that, or if we have 2 to 4 transactions per second, then we're way off the 600K that we need to be at. So we can kind of consider this out of the question. It's a bad option. If a candidate proposed this, I would probe deeper, even if they were mid-level. It's not a great answer. So if I probe deeper and I pointed out the limitations of that, then naturally a candidate might realize 2 things. One, if I'm going to use Postgres, then I need to be able to look up these proximity searches much more efficiently. And then 2, I need to somehow reduce my 600K TPS to something closer to 4 TPS. And so to handle the first one, you would introduce a geospatial index. And so a geospatial index is something that makes querying spatial data more efficient. And in this case, we would use a quad tree. And for Postgres specifically, it has an extension called PostGIS. And so quad trees, the way that they work, and let me maybe zoom over here and I have a little diagram that I can show. So the way that quad trees work is that they take a map. You can imagine that this is a map of the world. And they recursively split it into 4 regions. So imagine this first split here. And then we make this a tree. So here's our root node. This region is our red guy here. This region, green, blue, and orange, as you can see. And there's some K value. In our case, I've randomly chosen 5. And this K value determines whether or not we need to recursively split within any given cell. So in this case, we only have 3 drivers in this region of the world. And so we don't need to split them further. This is less than our K value of 5. Same 2 here and same 2 here. However, in this region, you can see there's a lot of blue dots. There's a lot of drivers. So we can recursively split again into fourths, as we do here, and then bang, add to our tree, 4 additional branches. And then we take a look at each of these respectively. So this one has 4. We don't need to go further. 3, 3. This one itself had 4, 5, 6, 7, which is greater than 5. So we recursively split it again, right? And so when you want to query, you simply walk down this tree, and when you get to any given leaf node, it should be the list of all of the drivers within that cell. So that's how a quad tree works, and that's what is a really popular geospatial index, and one that we can have supported here by Postgres via PostGIS. So that's one option. There's some pros and cons there. This is going to be linked in the bottom of the YouTube video, so you guys can read this on your own time as well. So that's great. We've now made the queries a bit more efficient. That's wonderful. But how do we handle these increased transactions per second? Well, sort of our only option there in this current setup is to add a queue here. And this queue would be responsible for handling all of these transactions coming in and then batching them to write in batches such that we can get this 600K down to 4K. And as you can see, this would be some pretty large batches. So obvious downsides to this are, one, we've introduced a significant amount of latency such that our location DB is now going to be mildly inaccurate because we needed to wait until all of these locations came in into a large enough batch for us to write them to our database. So that's not good. And then additionally, when we wrote to our database, because we're using quad trees, we need to re-index this entire thing. Right? So we have all of this new data that comes in. This tree needs to shift around. This is expensive as well. It also takes up a lot of space in memory. So there's some additional downsides as to why this is an okay option, but not a great option. If a mid-level candidate or even a senior candidate landed on this, it would be okay. Mid-level candidate certainly passing. Senior, I'd probably point out some of these limitations and then hope that they could go further. For a staff candidate, I have no expectation that you really have a deep understanding of these geospatial indexes. But again, I should be able to point out the limitations. You realize them and adjust accordingly. So this is not optimized, but this is an okay answer. Now, there's a better answer. And that better answer is that in order to handle these high TPS, we can make this an in-memory data store. Specifically something like Redis, which can handle anywhere from 100K to, if it's well optimized, 1 million transactions per second in a Redis cluster. So that's great. That handles that issue. And then from a geospatial index perspective, Redis supports something called geohashing. And so geohashing is a different algorithm that's used to do geospatial queries. And it's very similar to quad trees, but it doesn't require the maintenance of this additional data structure, this additional index. So the way that geohashing works, let me paste in a quick example here next to this one, is like this. So again, we split the region into 4s. You can imagine this is a map of the world. We split the region into 4s. And then we continue to just recursively split the region into 4s again. Now we don't make any determination based on K, so it's not density dependent. We just continue to split until we get to a precision value that we're happy with. So in this case, we have 0, 1, this cell is 2. If we split this cell 2 again, then we end up with 2, 0, 2, 1, 2, 2, and 2, 3 respectively. This is layer 2. Now we could then go again to a layer 3 and maybe take this 2, 0, and this 2, 0 will become 2, 0, 1, or 2, 0, 0, 2, 0, 1, 2, 0, 2, 2, 0, 3. Right, you get the picture. And this can continue to happen recursively. And so what you end up with is a base 32 encoding of this string that looks, something like this. And the longer the string is, the more precise, the more that final layer is zoomed into a smaller region. The less long this string is, the shorter this string is, the less precise, of course. And you can do things like look at just the first 1 character, 2 characters, 3 characters, and understand like the larger region that this exists in before you continue to zoom in. So this is how geohashing works. Redis supports geohashing out of the box. And so the benefits of geohashing, which are great for this situation, is that it's easy to calculate. It's relatively cheap to calculate a geohash. And it's easy to store. It's just a string. And it doesn't require any additional data structure. So when you're in an interview and you're having to make a decision between quad trees and geohashing, which might sound like some pretty obscure knowledge, but for what it's worth, for these proximity questions, Yelp, Find My Friends, Uber, this is kind of a place where you spend a lot of time and a lot of focus. So the question is often between quad tree or geohash. And the takeaway that I want you to have is that quad tree is great for when you have an uneven distribution or an uneven density of locations. So something like Yelp, for example, where you have a really dense New York City, but there's nobody in the Atlantic Ocean or nobody in the middle of Kansas, whatever. Then it's fantastic. But it's also required that you don't have a high frequency of updates because we don't want to re-index that tree on every single update. It's expensive. And geohashing, on the other hand, is indiscriminate as it pertains to density. The world is split into evenly precise boxes. So less good when you have an uneven distribution or an uneven distribution of densities of locations, but really good when you have a high frequency of writes. So in this case, despite the fact that our Uber drivers' locations would have an uneven density, because we have such a high frequency of writes, it makes geohashing the optimal answer. And so that's what we're going to end up going with here, is Redis and geohashing. And it's worth noting there are a couple other geospatial kind of algorithms, indexing strategies that exist. Uber actually uses something close to geohashing, but instead of it being squares, they're hexagons. I believe hexagons, maybe octagons. And this solves the problem that the distance from the middle of a square to the outside of the square is not the same as to one of its edges. So they've sort of made it more circular in that way. I think this was built in-house at Uber. So a couple options that exist, but these are the two main ones. The two main ones, if you know these two in an interview, you're totally set. If you can weigh the trade-offs between them just at the depth that I just described, you're in a really good spot. So now we've solved our problem of we don't need a queue anymore. A queue here would be over-engineering. We can easily handle the number of transactions per second into our Redis cluster using geohashing to then do these proximity searches. Awesome. Hopefully that makes sense. Okay. And then the other thing that I want to mention before we move away from location is that your interviewer might ask, 600K transactions per second is really high. How can we make that smaller? Like, do we need to overload our system like that in the first place? And this is a great question. We don't have to. There's no reason for us to do it every 5 seconds. We could make some product trade-offs on accuracy and say it's every 10, 15, 20 seconds, even up to a minute. But a more sophisticated answer would be that we could do this dynamically on the client. So the client could take in some information and be adaptive or send adaptive location updates based on things like the status. Is the driver currently accepting rides? Are they not? If they're not, then of course we don't need to know their location. The speed, are they parked? Have they been parked for 20 minutes? If so, their location isn't changing. There's no reason for us to send updates. The proximity to ride requests or hot areas. If they're out in the boonies, then maybe we don't need to send their location as frequently because we don't need this high of precision. So we can put this logic here on the driver and call this dynamic location updates. And this is going to make sure that this TPS goes way down. I'd still stick with the setup that we have here. But maybe we now got this 600K down to 100K or maybe even something smaller. All right, so that should cover that deep dive. Specifically low latency matching under 1 minute and optimizing for our location service and our location DB. The next one that we can look into then is consistency of matching. So this is where we want to make sure that no driver is assigned more than one ride at a time and no ride is matched to more than one driver. So there's two things that we need to consider here. Let me kind of paste those in to save the typing. So for consistency of matching, we can't send more than one request at a time for a given ride. And we don't send any driver more than one request at a time. So we're going to handle these two separately. So in our ride matching service, we're going to get that list of drivers. And so we have a list of drivers, list of eligible drivers. Maybe it's the top 10 drivers or so. And the way that we can handle this first one, making sure that that ride doesn't send out to more than one driver at a time, is really easy. This can just be logic within our ride match service. So we can simply have a while loop here that says, while we still don't have an accepting driver, go to the next one, send him a request, wait our 10 seconds, and then if we still haven't matched, go to the next one, send the request, etc. And this is because a single ride instance, ride matched instance, is only being handled, or a single ride that needs matching, is only being handled by a single one of these ride matching service instances, right? A single server here. So we can have that logic within that server, and it satisfies one pretty simply. I'll kind of paste in some pseudocode in a moment that hopefully will make that even more clear, because I fear my description there wasn't as clear as it could have been. But 1 is the easy one. 2 is the hard one. And 2 is the hard one because you need to remember that we have multiple of these. right? So in each of these cases, our servers are horizontally scaled. And so, yeah, you know, we have multiple instances of this ride matching service. And what you could imagine happening is that people just got out of a concert and the closest driver is the same for a lot of people. And those ride requests got matched on different servers here. And so each of these different servers said, give me who is the closest. And in each case, it returned a list that maybe looks like driver 1 and then driver 2. And so each of these instances, each of these ride requests sent a notification to driver 1. And in the case of a Taylor Swift concert, there's 100,000 people or whatever, then driver 1 is sitting there and their phone just went ding, 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 ding. They got 100 requests all at once. That's obviously bad. We don't want that to happen. So given that we have these multiple instances, there's nothing that we can do on a single box because we need coordination between the n number of instances here. They need to all see a similar state that a given driver is currently occupied. Okay? So what we could do is we could update a status here. We already had a status field in our driver. And so we can have an additional status maybe that says, request sent, something like this. And so when we get to driver 1 in our list, we would update this status and then send them the notification such that any other instance here that wants to send to driver 1, they first need to look in our database and see, was that request sent? This, of course, would need to be atomic. But we would check that, and then if the request was already sent, we would move on maybe to driver 2 because we know that driver 1 was already occupied. So this is very similar to Ticketmaster, actually, and how we handle no double booking for anybody who watched that YouTube video. If you haven't, go check it out. But very similar idea here. And if you watch that YouTube video, then you see the issue with this approach as well. And that's that we only want to send these requests for a certain period of time. We only want a request to be outstanding for, say, 10 seconds, maybe 5 seconds. A driver has 5 seconds to accept it. And if you've ever been in an Uber, you've probably seen this on their app. They have a pop-up that comes on their app. It has some loading bar that's loading quickly, about 5 seconds, and they have to click that button before that 5 seconds, or else we're going to go send that ride request to somebody else. So in this case, if we set this to request sent and the driver doesn't respond, they don't accept or deny, they're just currently driving, they're not touching their phone, whatever it may be, then this status is stuck. It's stuck as request sent. And for an indefinite period of time now, nobody else can send a request to driver 1 because they're stuck in this status. So we need some way to update this status. And so one thing that many candidates think of is that they want to do something like this. They want to introduce some cron job which runs every, n seconds or minutes, and it looks for drivers that have a request sent, and then we would need to have a status update time. And so we would basically do a query on this driver table to find anybody who's in a request sent status and to see if it's been 10 seconds since that status was updated. And if it was, update this back to available. And so this works. Like, this would absolutely work. But the issue with this, just like with Ticketmaster, and maybe even worse in this case, is that you're introducing some delta n from the time that a driver should have become available to the time that the cron job run. So if the cron job runs every minute and our delta here is 5 seconds, right? We only want a driver to be locked for 5 seconds, then it could take up to 55 seconds before we actually unlock you, when you should have been available to accept rides. And this isn't optimal. And in a case where things are really busy, we want to make sure that we can match you to the optimal driver to ensure that users have the best experience possible. So this is an option. It's an option that's great for a mid-level candidate. It may even be passing for senior, depending on how well you do in other areas of the design. But I would ask follow-up questions. It's probably not good enough for staff. I would hope that a staff candidate identifies the limitations here. But it is one option. A better option, just like with Ticketmaster, is to actually not do that and instead use a distributed lock. So this could be Redis. We could use the same instance here. I'll actually even talk about in a moment how it could be in the primary database, but just I want to make this clear by having it separate for now. And so we can have a Redis instance here, which when we want to lock a driver, all that we do is we set driver ID with some value, maybe true, and then it's going to have a TTL of 5 seconds. True. So this is just a key value pair. So we put in Redis, which is going to be a distributed lock in this way. We're going to use this distributed lock to say this driver is currently locked. So we'll add him to Redis, add driver ID to Redis. The value doesn't matter. I put it as true. Who cares? We're going to set this as driver ID, and we're going to set a TTL of 5 seconds. So in 5 seconds, that entry is going to be automatically removed from the cache. And so now what's going to happen is that anybody trying to send a request to a driver first needs to look to see if it's locked. So they'll check here. This is going to be really quick. It's basically just a hash map. They're going to look up that driver ID. They're going to see, does the driver ID exist in my lock? If it does, I got to go to the next one. He's currently locked. But if the driver doesn't respond now, this row is automatically removed, and the next person who reads this won't see driver ID here, and they can make a request to the driver ID. So this is fantastic. This is a distributed lock, very similar to what we did in Ticketmaster. It ends up working such that all of our ride matching services have a consistent global view of which drivers are available to send requests to. And it's wicked fast, snappy, great, etc. Now, you might point out, I have 2 Redis instances now. Why don't I just put this stuff here as well? You totally could do that. Another thing that you might want to do, which might even be smarter, is that this could be something like DynamoDB, which I think would be a good choice here. There's not a ton of relations. High availability is important. We can scale this largely indefinitely. And then we can introduce another table, which would be a driver lock. And this would just have the driver ID. And you can set in DynamoDB TTLs on rows on tables. So could end up doing something like that. Now, you don't need a separate, why is my text so much bigger? You don't need a separate lock here or separate a Redis instance to manage. You can just use the same database. Good consolidation. No need to introduce an additional technology, but we'll use this as the lock. So that's how we're going to handle the consistency of matching. And then just to make sure that this is crystal clear, I want to paste in here kind of what this would look like. So within this ride matching service, you would say, well, we don't have a match. Then the driver is going to be the next driver from a list that we got from our location DB. We're going to lock that driver by updating the driver lock in our database. And then we're going to send a notification to that driver to say, would you like to accept that ride? And then we're going to wait our 10 seconds. And so that driver might accept, they might deny. It's going to come through this path update. It's going to update our primary database, and their status is going to update to in ride. And so at this point then, no match should be false because there is a match. They're already in a ride. This is ended. Everything is good here. And then of course we'll have some way to notify the user, either by notification, polling, or otherwise, but I'm not going to go into a tremendous amount of detail there. Great, so those are certainly the 2 most important deep dives for this interview, but let's continue to make sure that we round this out. I recognize that the video is getting a little long as well. The next one I want to talk about is handling high throughput surges for popular events. So this one's relatively straightforward. What we want to do is make sure that we can scale dynamically in order to meet that demand. So if we had only n instances here, and then all of a sudden we had all of these people who want to ride, then maybe it's too much to be handled by these instances that we currently have. And we can't horizontally scale them dynamically quickly enough. And so naturally the solution to something like that, let's see if I can fit this elegantly into our diagram, is to introduce a queue. And so we can have a queue here. This is going to be our ride request queue. Ride request queue. Apologies that this is a bit tighter than I would like it to be. Okay. So we have our ride request queue here. And when rides come in, they're going to sit on this queue. And then our ride matching service is going to pull off of this queue in order to match drivers to riders for a given ride. So if we have a huge surge, no problem. We'll be able to handle that. It'll all wait in our queue here, and we'll just pull off when we're ready. Our queue is likely going to be partitioned by regions. So one issue that you run into with this queue is that if it's simply a FIFO queue, then you might have somebody who is the request came in first, but it's a much harder request to match. Maybe it's out in the boonies, there are no drivers around, whatever it may be. And then you could have some people who are stuck behind the queue here, not getting matched despite the fact that they're in the middle of New York City and there's drivers everywhere or something like this. Right? So that's not optimal. A couple things that we could do for that is that we would partition this queue based on location or based on regions. So within New York City, you would have kind of more fine-grained regions, even more fine-grained probably than the boroughs, but you would partition your queue on this. In this way, you don't have that problem where somebody ends up sitting behind a request that's taking a longer time to match. And then additionally, the added benefit here is that if any of these ride matching services go down, and remember, these are pretty computationally expensive, like they're waiting these 10 seconds, they're taking a long period of time. And so any of them could go down in that minute that we're trying to find a match. And if that happens, no problem. We'll just pull it off the ride request queue again. It won't have been acknowledged as succeeded. And then we'll continue to match that user. So this works pretty nicely. So the ride request queue, hopefully it's relatively straightforward. I won't go into a tremendous amount of detail, but that's how we're going to handle these high surges. High availability outside of matching. So this is where our system, it's kind of the traditional answer. We can horizontally scale each of these. These will have their own load balancers. This was DynamoDB, so largely it scales indefinitely. We talked about the scaling here from Redis, so that's great. The last thing is that we can split these by region. So realistically, we're not going to have a single instance of this full setup. Like maybe this is the Northeast region that you're looking at here. And then we're going to have a copy and paste of this entire thing out in California for, the Southwest region. Same with up in Seattle for the Northwest region. And these will be located in different data centers. Now there's probably things like users who can travel. Of course, you could go from New York to California, which we'll have in every data center, maybe just a read replica or a copy in the primary database of any given user table. But that's an additional way that we can increase availability, reduce the strain on the system, make things like the queue partitioning more streamlined and obvious by splitting by region here. All right, I think that just about wraps it up. Congratulations if you got all the way through it. Apologies, this video ended up being a little bit longer than I intended. Of course, as I mentioned, I went into more detail here than would be required in an interview, so I don't want anyone to feel overwhelmed. Just to be crystal clear here, mid-level candidate, if you got that high-level design and you were able to answer questions from your interviewer about some of the deep dives, you're doing great. Senior candidates, I hope that you could have gone deep in at least a couple of these places, the location service and ride matching, even if you didn't land on optimal with the distributed lock with TTL, but you landed on the cron job, or you suggested the queue here with PostGIS and quad trees, even if you didn't know the geospatial index. Probably great, very likely a hire. And then staff candidates, we do have that higher bar. Expect that you were able to show more depth in places, but maybe it wasn't the places I went deep. Maybe it's places that you understand even better than I do. And that would be great as well. So don't feel overwhelmed, but I wanted this to be relatively comprehensive so that you feel well equipped when you go into your interview. All right, with that said, thanks everybody for watching. If you have questions, comments, concerns, anything I did stupid that you want to call out, please put them in the comments. I'll be checking those out and responding frequently. This was the second of these that we've done. Again, check out Ticketmaster if you haven't seen that one yet. And I'll try to do another one here in the coming handful of weeks. All right. Thanks everybody for watching, and best of luck with your upcoming interviews. Take care.